to topics and statics. We're finally to the point where we're ready to talk about the equilibrium of a rigid body. We're going to do 3 videos on this. The first one, we're mostly going to introduce the conditions necessary for an object to be in equilibrium, and then we'll get a little bit more into the details in 2 and 3 dimensions in the next videos. So here's what we're talking about. We've got some rigid body with forces and couple moments acting on it, right? Here's the example with 4 forces, 2 couple moments, and I want to talk about whether or not this thing's in equilibrium. So what we just spent a whole bunch of time doing was figuring out how to simplify that system from the previous slide into just a single resultant force and resultant moment. And so there it is. That's how we do that. Then I pick some arbitrary point, and it doesn't matter where that arbitrary point is. It can be on or off the body. I can calculate the moment about A. I calculate the resultant force. The conditions for equilibrium about this point A is that the resultant force has to be 0 and the resultant moment has to be 0. In this video, we're only going to talk about this in 2 dimensions. Now, what makes something not move? It has reactions, not only forces applied to it, but it also has reaction forces, supports. Right? There are things holding it up so that it doesn't move. There's several different types of supports we're going to talk about. The 5 main ones are a fixed support, pinned, roller, link, rocker. A fixed support in 2 dimensions, a fixed support provides 2 reaction forces, x and y directions, and a moment. And it's going to prevent this thing from moving. That's what those are trying to do. If an object is pinned at a point, it has a pinned support as shown in this picture, then it produces just the 2 force equations, 2 force reactions. It doesn't get a moment. I can rotate it around that pin. If it has a roller support, all it gets is a force in one direction that's normal to that roller. That force can only point up. I can lift this thing off the roller. A link support produces a force along the link, only in that direction, and a rocker support produces a force only perpendicular. You'll understand how to use these better once we start working problems. So the whole trick to doing equilibrium problems is drawing a free body diagram. It's the single most important step. Right, step 1 is you figure out what is it I'm going to draw a free body diagram of. What object am I going to isolate it? Then I show all the forces applied to the system by mechanical contact with other bodies. Right, any body forces such as gravitational or magnetic forces, I add those. And then once I've got all the forces, then I determine how should the equilibrium equations be written. Right, forces on the free body diagram. The way to figure out these support reactions, if a support prevents translation in some direction, when the support is removed, it exerts a force in that direction. In other words, when I isolate the object. If a rotation is prevented, when removed, a couple moment is exerted. I never show internal forces on a free body diagram. I always assume the weight of a body is an external force acting through the body's center of gravity, G. I can put couple moments anywhere I want to on a free body diagram because they're free vectors. And forces I can put anywhere along their line of action. So the basic plan is you draw an outlined shape, show all the forces in couple moments. identify each loading, and give dimensions. So let's draw a free body diagram. Here's a nice little simple beam. All we're going to do is draw the free body diagram. So what type of supports has it got? It's got a pin at A, and it's got a fixed link at B. So free body diagram. Here's the beam. Let's start with the easy one. There's an applied force right here. I'm going to call that F1. It's got a fixed support at A, or a pin support at A. So that pin support will produce a force. Let's give it a different name. Will produce a force AY. Right, I can't move the left end up or down. And it'll also produce a force in the X direction. I can't move it left or right. Over here at B, it's got a fixed link, which is maybe that's not the best name for that. Let's call this right, because it's a fixed link, it has to pull. It's a rope. It's tied over there. So that has to pull on it. So that's a tension at B. And there's the free body diagram. The big thing to get out of that is looking at the support reactions. Let's try another one. Here's a beam. It's got an applied load. This applied load is a distributed load. It's triangular. So where's that going to be? This is going to be, we'll call that the resultant force. I can put where this is located. This is located 2 meters from the right end. I guess I could also calculate the magnitude of it. What's the magnitude? It's 6 meters times 4 is 2,400, divided by 2 is 1,200. This is 1,200 newtons. Now right in the center, it's got a support reaction. It's got a roller, so that only provides a force in the Y direction. At B, it's pinned at B, so I get a force this way. And I can have a force this way. If I want to get technical, I really need to define some distances. This is 3 meters. And that should be good. Now we'd have to figure out what those support reactions are. But I know what directions they point, etc. So next time we're going to take these free body diagrams and we're going to apply the conditions for equilibrium in 2 dimensions.